So do you remember all three of these techniques? Kind of? Elimination, substitution, and graphing. Okay. They're all good techniques. Sometimes one is better than the other. Sometimes you're not able to use one of the techniques. So for this first one, which of the ones do you remember the best? Substitution. Some people say elimination. So for this one, if I were to use substitution, can you see that I can easily get x by itself in the first equation? Usually something that tells me that I'd like to use the substitution technique is if I quickly look at my equations and say, is there a variable that's easy to get by itself? And if I get it by itself, that's not going to cause me to work with a lot of fractions or make my work messier. In this case, in equation 1 here, we can say that x is equal to 2y minus 1. So the way that the substitution technique works, then you go to your other equation, and where the x was, you substitute in the 2y minus 1. And now you've changed an equation that had two variables to an equation that only has one variable. So we have negative 4y plus 2 plus 4y equals 2. And this is a wonderful result because we get 0 is equal to 0. What does that mean? That's always true, right? And we didn't get y equals whatsoever. We didn't recognize right from the beginning that these two lines were exactly the same. We went to our substitution technique, and when we did that, we found out that 0 equals 0, which is always true. And in this case, because this is always true, there's an infinite amount of solutions. Yes? Did I? We would have seen that they're the same. Okay? Or if we would take both of our functions and rearrange them, say y equals mx plus b, because that's probably the way that you know how to graph lines best. If I would take equation 1, and I move the x over, so I get negative 2y equals negative x minus 1. Divide everything by negative 2, and I'll get 1/2 x plus 1/2. That's equation 1. Equation 2, if I move the x over, 2x plus 2, and divide everything by 4, well, 2 over 4 is 1/2, and 2 over 4 is 1/2. And I notice that both of those equations are identical. Okay? But the way the question was written to begin with, it was written so that you don't recognize that right away. You get into a rhythm of, I know how to solve equations. I use substitution or I use elimination, and you start doing them. What happens when you get these crazy answers where 0 is equal to 0? And then you all of a sudden feel like, well, now we know that that just means, since that's always true, we can smile. It's an infinite amount of solutions, no problem. On this one, we want no solutions. Or would you like to look at what would happen in the last one if we had used elimination? Okay, can do that quickly. If we had used elimination, you first have to pick a variable that you would like to eliminate, either the x or the y. Say you choose the x's. What I always like to do is I always like to get my variable, my coefficient in front of that variable, to be the same but the opposite sign, so you can just add them together. It's okay to subtract functions too. I find that students make more mistakes with negative numbers when they subtract than when they add. So in this case, I would take my equation 1 here, and I would multiply it by 2, and I would get 2x minus 4y minus 2. My equation 2, which was negative 2x plus 4y equals 2, when I add them together, I get 0 equals 0 again. Same result that I got with substitution. But that would be the elimination way to see that, yes, there are an infinite amount of solutions. Determine the value of k such that the following solution has no solution. Okay, what does it mean if there's no solution? The functions have to be parallel, so the slopes would have to be the same. So if we rearrange both of these formulas so they're in y equals mx plus b form, we would know something about their slopes. So starting with that, equation 1, if I move the x over, and then I divide by k, I find out that the slope of equation 1 is negative 1 over k. If I take my second equation and get y by itself, by subtracting kx on both sides, then I get y is equal to negative kx plus 4. If there's no solution, what do we know? We know that the slopes have to be the same. So if the slopes are the same, that means that negative 1 over k has to equal negative k. Solving this equation, multiply both sides by k, which gives us that k squared is equal to 1. So k has to be plus or minus 1. The one thing I would do with this, though, to check is just to make sure that by plugging that value of k in, I don't also get the same y-intercept. Because if I happen to get the same y-intercept, then there would be an infinite amount of solutions. Now our y-intercept for our second equation up here is just 4. And it doesn't matter if I plug in 1 or negative 1 in for k here. My y-intercept of my first equation is either going to be 2 or negative 2, which either one of those will make it have no solution. Another one for you to try. You get to choose elimination or substitution. Most people don't like the graphing solution. Graphing only by hand without a calculator only works nice if the points intersect nicely. Hello?
Sorry for interrupting. Could you please have Hillary finish the office?
A couple of things that I would do in a question like this. I notice it has fractions on the bottom of the first equation. Life is always easier when you're not working with those fractions as far as your mental math and adding and subtracting goes. So what I would do first is I would probably take this entire side and this entire side and multiply them by 6 just to get rid of the fractions. So that would have changed my first equation to be, well, 6 divided by 2 is 3, and when I distribute that, I get 3x minus 3. 6 divided by 3 is 2, and I distribute that, I'd get 2y plus 4 equals 24. And now my equation is easier to deal with. In fact, I can combine like terms. If I make everything go on one side here, I'd have 3x plus 2y and subtract 1 on both sides is 23. At this point for solving, when I look at both of my equations, I notice right away that my 2y and my minus 2y are the same. I would probably lean towards elimination. So when I write the equations on top of each other, I notice I can add them right away. And so 4x is equal to 28, and I can figure out that x is equal to 7. Once I've got x is equal to 7, I get to plug that back in to solve for y. I look at my original equations, and I decide that it's obvious that the first one is much easier to plug x equals 7 into as opposed to the second one. Okay, yeah, I'll plug it into the second one. 7. And we get 2 is equal to 2y, y is equal to 1. Those are our two answers. You can write your solution as a point as well to show that that's where we would have the intersection, 7, 1. Have you ever solved systems of 3 equations with 3 unknowns? Some yes, some no. The idea is similar to what we were doing before. What we did in the last equation with either elimination or substitution is you worked out things so that you had an equation that only had one variable in it. Well, the same thing's going to happen here, but we first have to work out things so that our equations have only 2 variables. So we're going to start with 3 equations with 3 unknowns. We're going to use elimination and substitution, or a combination of those, to get down to 2 equations with 2 unknowns. And then we'll be able to solve it like we did before, either with substitution and elimination, until we figure out one variable, and then slowly plug that variable back in until you find out all 3 of them. Okay? Now, what you're going to do, we're going to number these because it's going to help us organize things. And for the most part, we're going to use elimination. I know that we've already got the second equation without a z, but I'm going to tell you I'm not convinced that z is the easiest variable to eliminate. Because if I was going to eliminate z from my other equations, 1 and 3, I'm going to have to multiply equation 1 by 5 and equation 3 by -3. That's going to get my numbers a little bit bigger. Sometimes when I'm looking at which variable I'm going to eliminate, I'm looking at which one I'm going to use the smallest numbers possible to eliminate, and looking at these, I'm thinking x would probably work the best. Now, I need to eliminate x. I can choose any 2 equations to do that. I'm going to start by choosing equation 1 and equation 2, because if I rewrite those, I notice that my coefficients, and I'll leave a space there for the z, that my coefficients are already opposite in front of x. So if I add these 2 equations together, I get y plus 3z is equal to 5. That equation has no x. I'm going to call that equation A. I was using numbers for my first. I'm going to go to letters for my second one. Oh, and this was equation 2. Equation 1 and equation 2. Now I've eliminated x using equation 1 and equation 2. Now I'm going to try and eliminate x either with equation 2 and 3 or with equation 1 and 3. I get to choose. And it doesn't matter which one you choose. Just choose something that you think would be the easiest. Looking at this, I'm going to choose 2 and 3, and I'm going to multiply my equation 2 by 2, so that my coefficients of x are going to be the same but opposite signs. So when I take equation 2 and multiply it by 2, I'm going to get -2x plus 6y equals -8. And equation 3, I'm just going to rewrite 2x minus 5y plus 5z equals 17. Now when I add those together, that's 0. This is just going to be y plus 5z equals 9. That's going to be my equation B. So what I've essentially done is I've started with 3 equations with 3 unknowns. I've used some elimination. I chose a variable to eliminate. And once I did that, I'm down to 2 equations with 2 unknowns. With A and B, if I take those 2 equations, and let's say I rewrite equation A, y plus 3z equals 5. I take equation B and multiply it by a negative. -y minus 5z equals -9. And add them. I get z equals to 2. which makes sense because often when you make a z, it looks like a 2 anyways, right? From there, we can go back and choose either equation A or equation B to plug in z equals 2 to figure out what y will be. So if I choose equation A, I get y equals to -1. If I had chosen equation B, quick mental math and looking at it, you'll see you would have got y equals -1 there as well. It should work out to be the same one because we're trying to find the point where all of these intersect. Now we can go back to equation 1, 2, or 3, plug in y and z, and it shouldn't matter which one we choose to find the value of x. Which one would you like to choose, 1, 2, or 3? 2? So 2, -x, you don't even have to use what z is in this one, plus 3y, plus 3 times -1 is equal to -4. X is equal to, add 3 to both sides, -1, so x is equal to 1. So our solution, and what each of these things were that we were working with, they were lines in 3 dimensions, and all 3 of these lines intersected at one point, and that point where they intersected was 1, -1, 2. So you could extend this now. If you started with 10 equations with 10 unknowns, you would choose one variable and eliminate it. And then you get 9 equations with 9 unknowns, and then choose another variable and eliminate it, till you have 8 equations with 8 unknowns, and then choose another variable and eliminate it, until you have 7 equations with 7 unknowns, and then 6, and then 5, and then 4, and then 3, and then 2, and then finally you find one value, and then you plug it all back in until you find all the values. Of course, this gets tedious, and when things get tedious, mathematicians think up of new ways of doing this to make it easier. I'll say easier. Notice I didn't say it less tedious. We will still have a tediousness in this unit. I should almost call it, instead of linear algebra, linear tediousness. And but for now, that's where we're going to end today. And you have that worksheet to work on.